Good morning, everybody. My name's Carl Griffith from Graybar. I work at our corporate marketing department, Director of Emerging Technologies, and I want to welcome you to our seminar today, our G2 Talk seminar, where we will have a presentation from Corning talking about fiber optics and energy conservation inside data centers. So we want to welcome you. Before we begin, though, I thought it would be important for us to describe a little bit about what Graybar does. Graybar is a distributor in the marketplace providing the materials to construct, redesign, or rebuild a data center. Graybar's mission or statement is on the screen there, that we help our customers power, network, and secure facilities with speed, intelligence, and efficiency. So some of the things that we would provide into the data center would be power distribution items, communications connectivity items, cooling items, lighting, security, automation, all the things that you would expect that would apply to the infrastructure inside a data center. So we want to welcome you to our seminar series today, G2 Talk seminar. We've done about 4 or 5 of these, and we do one on data centers the third Thursday of every month at 10:30 Central Time, so we're glad you're with us. The first 50 people that logged on and are here for the seminar will receive a cup of coffee, courteous of Graybar, a gourmet cup of coffee at that. So we'd want you to check your email a little later today, and we'll pop you an email and the instructions there'll be instructions in the email that show you how to redeem that for a cup of coffee. The other thing is as we go through our seminar today, you'll have the opportunity to ask questions. So on the screen you have a little QA box there that you can type your question in, and we'll get that question here, and we'll make sure we get it to our presenter, and we can have some conversations either throughout the presentation, or there'll be actually a Q&A area at the end where we can dive in and get a little more deeper to help you with your questions that you may have. So without delaying any further, what I'd like to do is introduce our speaker to you. His name is Eric Kleiber. I've known Eric for quite some time. We've done seminars around the country together and about data centers. And Eric is the data center marketing specialist for Corning Cable Systems. He's in Hickory, North Carolina. And I'd like to welcome Eric to our G2 Talk, and we'll let you go and talk about fiber optics and saving energy, Eric. So I'm going to turn the baton over to you.
All right, thanks, Carl. Thanks for having me today, and look forward to doing this. So what we want to talk about today is basically how fiber optics helps you not only be eco-friendly, eco-conscious, but also be more efficient in your data center, which helps you save money. In reality, when we start looking at things to go green, green can be twofold. Green can be for the environment, and green can also be for your wallet. So let's look at what we're going to be talking about. And what we want to really look at is how does TIA 942, which if you've ever done any design work or any build-out work in a data center, that is your go-to source for how to lay things out. And then we want to look at what is actually the problems that are occurring in data centers today that would start to lead us into this green data center environment. And then how do we do that? So once we get the problem, we're going to want to look at exactly how this is done in order to make a more efficient, a greener data center. And the big thing here is we want to look at the structured cabling impact of how these energy savers in the data center, how we impact that with our structured cabling environment. And at Corning Cable Systems, we sell both the hardware, the cabling. We do the tip-to-tip solution that allows us to do some of these energy savers, and you'll see some of those products throughout this presentation. And the last thing is a statement from the U.S. Department of Energy concerning data centers. Recently, there was an article written in the New York Times about how much energy data centers actually use, and it's actually mind-blowing. Most data centers use enough energy to power, hundreds of thousands of homes, and we don't even think about them until something like Sandy comes through and knocks the power out. Well, how do these things get the power to run their mission-critical facilities? So we'll talk about how we can reduce the amount of power and how some companies are actually going greener with their backups. So what is a data center? A data center is defined by the TIA 942 standard as basically a building or a portion of a building in which computers are housed. This is typically, in the past, we've seen anywhere, they used to be called computer rooms, but now what we started to see is even small rooms such as telecommunication rooms can be considered data centers. Each of those have now this can range from, like I said, a telecommunication room up to 100,000 or greater square footage building that's completely dedicated to a data center facility. Each of those has their unique complications and unique challenges, but in the end, you still have to power it, you still have to cool it, you still have to network it into your actual business. So the function of a data center is basically to consolidate all of the IT resources into one spot. Typically, we don't do a one-spot data center for the simple fact that we don't want a single fault. So if something that comes through, like Sandy came through the Northeast, they knock out a data center. Things like let's see what failed. Small things like Tumblr and some other websites that people rely on every day to interact with other people. Those no longer worked because of the fact that there was only one spot for it. Now, what we typically do is we see redundancies across different locations. But it still consolidates the resources into one or two locations. Of course, it houses the network operations, and if your company has an e-business sort of front, such as Amazon, eBay, any of the sites where you can actually order off of, that's a revenue-generating function. So you want to be able to have a facility that can maintain that mission-critical processing. Case in point, again, with that Sandy, the data center, the backup generators were on the upper floors, so they were not harmed by any of the water, but the pumps that feed the diesel to those generators were in the basement, and they flooded, and so when the power went out, there was no way to get diesel up to the generators to power the data centers. So they were actually using 5-gallon buckets, one in each hand, and going up 14 floors of stairs to basically do a bucket brigade for these mission-critical functions. Now, that all being said, what are the actual problems that's happening in data centers in terms of power? What we see here is a power consumption, and the biggest chunk are those associated with heating and cooling, well, not necessarily heating, but cooling of the facilities. When we start looking at this, what we want to do is reduce the overall total energy consumption. The big thing now is CO2 emissions, so the less CO2 emissions that we can have overall in the data center, the better. But what we want to do is we want to start shifting the amount of energy that we use for the cooling units and start putting that over into what we call revenue-generating loads. These can mean more servers, these can mean more switches to better facilitate a faster retrieval time of data. People like Google and places like that, they measure their latency to a search in the milliseconds. So if you can facilitate that through better switching or better servers or even better storage, you can actually better serve your customers while still having a lower overall total energy consumption. So we really want to shift that power away from heating or away from the cooling environment and into the revenue generating. So this is the top 12 energy savers for data centers from a source called Energy Star. Energy Star does like appliances, they're Energy Star qualified. We have not seen LEED come out yet for data centers, but LEED is actually being developed for that. But what a lot of things that I'm seeing is people are not going to design to the LEED standard. They're going to design to the standard that makes sense, which is, yes, it's energy efficient, but not necessarily LEED certified. So there's a couple things here that we want to look at. What the 4 things out of the 12 that a fiber optics can directly affect. So how can we do the energy savers for data centers? We can invest in technologies that save energy, which are, we'll talk about that, the advantages of different data center layouts, how you contain and enclose your servers and switch racks, and then, of course, general airflow. There are a lot of other things on here that are just as impressive or even more impressive. The virtualized servers is definitely occurring. If you have a server that's not doing any data crunching, but is still up and running, you are still having to power it, you're still having to cool it. So that's one of the biggest ones. And then what we're going to talk about is things that are coordinate cable systems and fiber optics can definitely impact. So let's look at investing in technologies that save energy. So what we want to really compare is copper and fiber ports in a switch, or copper and fiber in general. And what we want to look at is 10 gigabits. That's pretty much the most deployed speed today. We do see some 40 gigabit and 100 gigabit Ethernet coming online, and there is still legacy 100 meg, 1 gig things around. But the majority of data centers, either being new builds or retrofits, are upgrading to the 10 gigabits as more bandwidth is consumed either at the desktop or in everyone pretty much has smartphones now, so even that sort of thing back at the head end of the facility needs to have the ability to create more data and pass at higher bandwidth. So again, the 10 gig is pretty much the standard that's out there right now. And what we see is with copper, the ports themselves actually have to produce more power. They have to use more power to transmit the same signal over the copper medium. So your power consumption for copper is anywhere between 4 and 5 watts. And what we've seen is, regardless of the distance that 10 gig is going, the minimum power wattage that we can use is anywhere between 3 and 4. We'll never see anything below that. So compare that to fiber. Typically on a short multi-mode run, you're looking at around 1 watt per port. Whereas if you were looking at distances for single-mode fibers where you're going from building to building or up 7 stories in a building, distances that are further than multi-mode can handle, the lasers are a little bit more powerful, and so they require more power to operate. So that's where you see that 4 watt come in. But again, that is not the typical. Typically, multi-mode is used in our data centers within the actual data center itself, just because of the distance limitation it has. So you use the VCSEL, which has a much lower power wattage than the copper. So let's look back at copper now. As you pass that signal down which is an electrical signal down your copper cable, that copper becomes warm. So as you just in simple physics terms, I say simple physics terms as it's simple, but it's not really. But as you pass current down a wire, it heats up just because of energy loss. And what you see is actually you have to start cooling that as well. So that adds to the overall heat generated inside your data center. The transceiver side in copper is typically larger than a fiber transceiver. And then because of that, because we have larger transceiver size, we have less ports that we can put in per blade, which means we need more switches, which means we need more data center area. So the larger the data center area you have, typically the larger crack units you have to have in order to cool it, in order to push the amount of volume of air through your data center to make sure there's no hot spots. On the fiber side, even though there's optical loss that does occur, it does not generate heat. It is all done through light. Light is the only thing that's lost. The transceiver side is small, which leads to higher densities, which means lower data center area for the same amount of information being passed through. What we've also seen here is that there's estimates that 60% of all data center downtime, whether that's unscheduled downtime, typically a server gets too hot, it shuts itself down, and you no longer can access your email, and you get frustrated and you call your tech support and you say, why can't I answer my email? Typically those are related to heat. So if you have a hot spot in your data center, that heat, that air is being sucked into this server, gets too hot, it shuts down the server. So that is what we really want to look at, is the amount of how to cool that and how to make sure that we're not putting too much heat into our actual data center. So we want to look at here, this is, again, comparing copper and fiber, both 10G networks, and the electronics operating power. So this is the power that actually goes to doing the switches and everything else that's done in the actual network. You can see just because of that wattage difference per port, you can see that there is a substantial savings going from copper to fiber. So copper is more expensive, fiber is less expensive. So this is a yearly savings. This isn't just an upfront savings. This is a yearly savings. So this is compounding. So the longer you run your data center, the more money that you'll save. Sort of like refinancing a house. When you upfront, you might have to pay a little more extra cost, but what happens in the end is you end up paying less interest. You end up paying less money every single year. So what we see is, then we look at the cooling. So because that copper is producing heat, we need to cool it as well. So we actually see even more savings on the cooling versus the power. And we can actually see, when you add those two up, somewhere in the range of $11,000 of saving per year. Now this is, I do believe, on a 10,000 square foot facility. And we're also estimating at 13 cents per kilowatt hour, which may be very generous in some places and may be very cheap in others. Just depends on your power, who's producing your power, and what the deal they're giving you. So again, 55% overall energy savings when you look at a fiber optic plant versus a copper plant for 10 gigabit. So now let's look at that in a bar chart, and we see that the copper is more of the purple. The fiber looks like aqua there. Those are the bars, and then you have the energy savings in your yellow line there at the top. So as we go to higher and higher data, higher and higher switch ports, from 48 up to 288, we actually start seeing an increase in the savings and the increase in the percentage comparing fiber to copper. So if we look at the 288 fiber example, we're looking at 32,000 annual savings, and again, this is assuming 13 cents per kilowatt hour, which is a national average for power supplied to data centers. All right, so now let's look at taking advantage of different data center layouts. In the past, we've kind of ad hoc thrown in rows and rows of cabinets that really didn't. They were all facing one direction, so you knew which side was the front, which side was the back, because as you walked down. What we realized quickly, though, is that in order to improve our cooling efficiency, what we've done now is gone to what we call a hot aisle, cold aisle architecture. And this is based on TIA 942. Again, so what we look at is in a raised floor environment, the crack units send cold air underneath the floor, and they come up through perforated tiles in what we call the cold aisle. The servers the fronts are all pointing in towards that cold aisle. They suck in the cold air and they blow out hot air. And as that happens, that hot air then gets returned into the crack units, whether it's through a above plenum space or if it's just let to wander back into the crack units. And what we see here is that the fiber optics is really an enabler of airflow within these sorts of architectures. If you look at the right picture there, this shows that there are 48 Cat 6A cables, and these are quote-unquote reduced diameter cables, are required to serve the same amount of number of ports as can be served by a cable that's only 0.58 inches in diameter. And so you can see the amount of air blockage when I need to put that much copper cabling in, not including the amount of weight that copper cabling has, but just the air blockage is able to stop this sort of hot aisle, cold aisle from working efficiently. So here's a better look at a raised floor environment. And what we see here is on the left-hand side, it's a depiction of a copper cabling. So this is a 2D fiber or 2D copper model, and the right one is a 2D fiber model. And what we're showing here is air velocity. So the redder the arrows, the higher velocity it is. And what we're seeing, the right one, the fiber tray, has the amount of cabling needed to facilitate what the left tray with the copper in it is doing. So we're not sacrificing port counts. We're not sacrificing bandwidth. In fact, we're probably increasing bandwidth. But what we see is the amount of air blockage that the copper cabling can do. So what does this also mean for the green in your pocket? Well, the U.S. Department of Energy recommends at least 24 inches of unobstructed pathway for air to flow correctly underneath a raised floor. So if you start stacking these copper cabling in, you may have to go from a 24 inch raised floor to a 36 or a 48. I've even seen them where you can actually walk underneath the raised floor. So that adds a significant cost to your actual building, to your design, and everything else that needs to go into working for making sure you have the correct airflow underneath in your plenum space. So you're basically doing a 30% reduction in the air blockage just by going to fiber in your underfloor cabling space. Inside each rack, so when we start doing this hot aisle, cold aisle sort of thing, what we see is we have to pass cold air, and you can actually see this is from Schneider Electric here. Cold air is coming in the front, going through certain things, and then going out the back. Now, those certain things we want to be the electronics, because that's what needs to be cooled. If the electronics aren't cooled, if the air is just passed through, it's doing no work. And what we really want to do is the energy we put into cooling the air to go into our data center, we want to have that be able to perform some work by cooling the actual servers and actual switches that are doing all of our revenue generating within our data center. So what you have to have is you have to have the ability to block the airflow in all other spots other than what you want the air to pass through. And so you need a set of hardware that allows you to block it. So you have to have an enclosed set of hardware. So now we want to contain your actual hot aisle and cold aisle. So there's different ways to do that. You can do chimneys. You can do regular hot aisle containment, cold aisle containment. It doesn't really matter as long as you're doing containment. You really want to see a reduction in the amount of cabling bulk within the cabinet. You need to have you have less rack space needed in each switch cabinet for your actual terminations, and then you actually get improved airflow for switch cooling. And so that's what I want to go to next. This is a picture of, these are two pictures of a Cisco 9513 with the maximum amount of fibers connected to it, which is 528 fibers. Actually, it's over 1,000 fibers, but because there are duplex patch cords there. So what you see is the amount of bulk that the cabling jumpers can block airflow. This is a side breather, so we have to have air come from the left and go to the right. And the one on the right-hand side is actually the harnesses. So the harnesses allow you to get better airflow, have ease of connectivity, and they don't you can actually pull a switch out without affecting any of the other switches, or without any of the other blades, which is difficult to do with the jumper solution on the left. Last one is the review general airflow. So when we look at this, what we really want to do is use high-density hardware to reduce the overall footprint. The denser you go, the smaller area you have to cool. So typically you put the crack units on the walls, and you pump the air, and you have to be able to pump it fast enough and with enough air velocity to get to the furthest point that needs to be cooled at the temperature that it needs. So by going to a smaller, a more dense footprint, you're able to reduce that overall total footprint and use smaller crack units. You want to reduce the bulk cabling. You want to reduce the patch cord bulk in front of and between switches. And then you need to improve the access to the switch ports and blades so that even those can get sufficient air. So here's the last thing we want to sum up with. This is from the U.S. Department of Energy, or the Federal Energy Management Program. Here's where it states that the minimum effective clearance is 24 inches, should be provided for all raised floor installations. You need to have a cable management strategy to minimize the flow of air throughout your entire data center. So you need to have this strategy put in place when you're designing the airflow. And you're designing the actual overall data center, how much crack units you need, or how many crack units, how big those crack units need to be, what your chiller temperature going to be. So there's a lot of things that go into not only deciding between copper and fiber. Again, the fiber has the lower port per port wattage, and the overall fiber itself, even though there's loss occurring, doesn't create heat, whereas copper does. So the less copper you have in your data center, the smaller the crack units can be slightly. The big efficiencies you gain there are with the hot aisle and cold aisle containment. So that's all I've got today, and I'll send it back over to Carl.
Thank you very much, Eric, for a wonderful presentation. And we want to make sure we have some time to respond to your questions. I've received one question from Fred wanting to know whether parts of this presentation will be made available, and we will make the presentation available. You can go up to graybar.com and get it there. In particular, Fred, I'll look up your email address and make sure I send it directly to you as well to make sure you have it directly. But for others that would like to have a copy of this presentation, the associated documents that go with this program, or even review this presentation, they can do it at graybar.com. There were a couple questions that came in, Eric, and I wanted to fire them your way. When we talk about the airflow underneath the floor, and we looked at the size of the copper cables versus the size of the optical fiber cables, questions come in about has Corning done a study looking at cables that are routed overhead as opposed to cables that are routed under the floor?
So we haven't done a actual study on overhead per se, but the same results apply if we start looking at contained plenums overhead. Typically, the data centers that I've gone into, they literally are completely open above, and so any sort of hot air going up is literally just dumped into this general space. If you do a contained hot air plenum where you're pumping the plenum or hot air back to my return units, if you start putting things in the way, it would apply directly to the same underfloor arrangement. So you still have to have the airflow go through. You still have to limit the blockages. But typically we see the hot aisle, or typically we see the cable trays hung below that plenum space anyways, so that there's no blockage anywhere up there, whether it be copper or fiber. So there's really not been an impetus for us to actually go and do a study on that, just because of the best practices that are already employed in data centers.
So in summary, we could say that obstructions on the return side are just as important as obstructions on the intake side, correct?
Absolutely.
All right. And then the other question is that the study that was presented in the very beginning of the presentation that had to do about energy consumption on copper ports versus fiber ports, I'm assuming that we were reading data tags on blades. So when we populated the data center for this study using optical fiber blades, and then they were replaced using copper blades to get the numbers, that's how that math was done, correct?
Yes. So what we're actually looking at is the actual power consumption. There's many things out there that can actually pull the amount of power from that's being consumed by the switch in general. But we are actually looking at a per port wattage, and that is done by the transceiver. So the transceivers have wattage ratings, and that's what we're actually pulling from.
All right. So can we say that on the server side of the equation, if we're using the optical fiber port on a server as opposed to a copper port on the server, we're going to get a little bit of savings there as well, too?
Absolutely, 100%.
All right, great. I'm going to make sure that we give everybody that's online an opportunity to ask a question. If there's anybody that has a question online, if you want to type it in the Q&A box right now, we'll be sure to lift that up to Eric. While we're waiting for some more questions to come in, I wanted just to remind everybody that the first 50 folks that were on this presentation today are going to get a gourmet cup of coffee courtesy of Corning and Graybar, and we want to make sure that you check your email after this presentation, and it'll give you the instructions on how to do that. We want to thank you for participating in our seminar today and joining us here at Graybar on our G2 Talk seminar. The other thing I want to mention is if you have a topic that you would like to see us to cover on our G2 Talk series, if you want to type that in the Q&A window, we'll leave the window up here for a minute or two. You can just go ahead and type that in, and we'll try to find some resources to respond to a topic that you would like to have us present. So we'll give you that opportunity to do that in the Q&A. Thank you very much to Corning Cable Systems for being our presenter today. Especially we want to thank Eric for your time today, and thank all of you that attended the seminar today. We'll see you the third Thursday in December for another presentation in the data center space. Thank you very much for your time, and have a great day.